before we write the codes for building the computational graph, let's take a look at the graphic representation of the neural network. We will start by using just a single softmax output layer. That's the top layer here, right? And then a single input layer. Right. For now, let's not add any hidden layers yet. Right. And later on, we're gonna add more hidden layers in the between the output layer and the input layer. But for now, let's just deal with this kind of very simple setup. Right. So the softmax layer is gonna have 10 output neurons with their logits denoted as Z0, Z1, Z2 up to Z9, and then their outputs denoted as Y0, Y1 up to Y9, right? And we talked about the statistical interpretation of the neuron outputs Y0 to Y9 in the 8th video. We can understand why I, so suppose the subscript is I here, right? We can understand yi as the probability of the input handwritten image being the digit I, right? So if yi denotes the probability of the handwritten digit being the digit I. Right? So every input is connected with every output, right? And here we have added one more. We have added one more input with the value x0 fixed at 1, which will account for the bias term. We also did the same thing when we were doing the linear regression problem. But here we are also adding this particular neuron that's going to account for the bias term. And then x1, x2 up to x784 is going to be the flattened input image of the handwritten digit. And then this x0 denotes the bias term. Right? So let's first take a look at the logit z0, this particular term. So if we denote the weights that's associated with all the connections that's coming into Z0, right, as WI0. So WI0 is going to denote the weights associated with all the connections that's coming into this particular neuron. Right. Then we can write the logit Z0 as the weighted summation of all the 784 inputs that goes from x1 to x784, right? And also x0, which has a value of fixed value of 1, multiplied with w00. Here. You can think of w00 as 1 multiplied w00, right? And this 1 comes from x0. So basically, z0 is going to be a weighted summation of all the inputs with their weights given by wi0, and I goes from, in this particular summation, it goes from 1 to 784, so it counts for these inputs, the inputs x1 to x784, and then plus w00. Right. So for logit z1, we can denote the weights associated with all the connections coming into this neuron. Right. I didn't actually draw all the arrows because there are just too many arrows to draw, so I was being lazy. Right. So for the logit z1, we can sort of denote the weights associated with all the connections coming into this particular neuron as wi1. Right. wi1. And then I goes from 1 to 784. Right. If you account for I being 0, then we have another term that's w01. That's going to account for the weights for this particular connection. This particular connection, right? So from x0 to y1, to z1 basically. Right? And the one thing that we have to sort of pay attention to is that xi, right? So all the xi is actually identical between these two equations. Right? It's the same image, it's the same input image, and the same bias node x0, right? So xi is sort of identical. The only difference is wi0 and wi1. They are sort of a different set of weights. And in total, if we write this kind of logic for every output neuron, then we're going to have 10 equations, right? We are going to have 10 such equations for 10 logics in the output layer. And the weights for each layer are just denoted as WI0, WI1, right? And then WI2 up to WI9. So with the I goes from 0 to 784. If you want to separate out the weights for this bias node, then I goes from 1 to 784. It's not 0 to 784, but the 0 term goes here. Right? And so suppose we have one training image, right? We can write these 9 equations in a more compact form if we actually use matrix vector multiplications, right? So here I'm just talking about logics, right? Logics are linear expressions, right? And then once you got the logics, you can compute y. You can compute the neural output y by using this particular expression, right? You just take the exponential of the logic and then divide it by the summation of the logic, exponentials of the logic over all the 9 output neurons, right? So once you got the logic, you can compute yi. So let's not concern ourselves with this particular step from the logic to the output. This step can be computed very easily in TensorFlow. It's just involves one function call basically. So suppose we have like one training image that has been converted into this one row 784 column vector, right? And with elements that goes from with elements x1, x2 up to x794, right? And then we can put all the weights, all the weights for the connections that go into the first neuron on the first column. So the column, it's going to be the first column is going to be W10, W20, W784. It's the weights that's associated with all the connections that goes into the first neuron. That's WI0 here, right? It's WI0. So I goes from 1 to 784, right? And then the weights associated with all the connections that goes into the second neuron is going to be on the second column, right? So the second column is going to be WI1 basically. That's WI1 here, and I goes from 1 to 784. And so on and so forth. Then this weight matrix is going to have 10 columns associated with the 10 output neurons, right? So the first column with the second subscript 0. The second column is going to have a second subscript 1. And then the last column is going to have a subscript 9. Right, second subscript 9. That's going to correspond to Z9, the weights for all the connections that goes into the 9th neuron. Right, the last neuron basically. That's WI9. I goes from 1, 2 to 784. Right. And then if we actually carry out this matrix vector multiplication between this input vector of image, the input image vector, and this matrix of weights, we're going to obtain a row vector with just 10 elements, and each element is actually the result of this weighted summation in each of the 10 equations, right? In each of these 10 equations. And then we can add this row vector containing all the row vector that we just obtained with the vector, this vector that contains all the bias terms for the 10 equations. So W00, W01, W02 up to W09, W00, W01, W09. Right? And the results are the 10 logics, Z0, Z1 up to Z9. Right? So this part of the long equation, the big equation, this part of the big equation is pretty much just a straightforward translation of these 10 equations that's written here. But this summation with the row vector and the 10 bias terms can be sort of absorbed into the matrix vector multiplication if we add a number 1 at the beginning of the input image vector, the row vector of the image, and then move these 10 bias terms to the top of the weight matrix. So if we just put this vector on top of this matrix, right? So W0, 0, W01 up to W09. This top row is the bias here, the bias vector here. If we just move this row on top of the weight matrix, right? And then we add 1 in front of it, and this 1 is going to account for x0 basically. So you can just replace this 1 with x0, then that's the same thing, right? And then all the weights on top of the on the top row of the weight matrix are going to be the weights that's actually coming out of the weights for the connections that's coming out of x0 basically, right? So if you do this kind of thing, these two approaches are going to be identical. So if you do this vector matrix multiplication, you are still going to get the 10 logits. They are just the same calculation expressed in a different way. And this second approach, is actually what we did when we were solving the linear regression problem. And in that problem, the weight matrix had only 1 column instead of like 10 columns here, right? And the input vector had only like 3 elements, including the leading 1, right? If you don't exactly remember how that code was written, so we have a matrix that's called input data with bias, and we did a concatenation of a column of 1s, right? MP 1s is going to generate a column of 1s. How many rows? N rows, and then 1, right? And then that's the input data, which is actually equivalent to concatenating, putting a 1 in front of it, in front of every input vector. Here we have just one training set. If we have like multiple training sets, then it's a column of 1s. It's a column of 1s, right? And then in the linear regression example, the weights is just a single column, right? The weights is just a single column, but it's n co plus 1, right? The 1 actually accounts for the bias, W00 basically. So now let's try to check the dimensions of each matrix and vectors in this big equation. And if we understand how the dimension actually works out, we understand how to write the codes. So if we denote the input image as capital X, it is 1 row, 784 columns, right? 28 by 28 pixels. And then the weight matrix without including the bias term, right, which is denoted as capital W here, is 784 rows and 10 columns. So this multiplication is going to produce a vector with 1 row and 10 columns. And this vector containing all the bias terms, which is denoted as B here, is also 1 row, 10 columns, right? So this kind of component-wise summation, this summation is going to work out, right? Because the result of this multiplication is going to be 1 row, 10 columns, and this B is also 1 row, 10 columns. So if you do this summation, component-wise summation, it's going to work out all right, right? Which are the, and the result of the summation is just going to give you 10 logits, the 10 logits, 1 row, 10 columns, right? It's Z, which is 1 row, 10 columns. And if we, this is sort of the first approach, right? And that's the approach that's adopted in our code for using TensorFlow, right? We're going to use this approach, right? And then the second approach, if we take the second approach, right? If we take the second approach, which is to add a 1 to the beginning of the input image vector, and then to move all the bias terms to the top of the weight matrix, right? Now we have a vector that's one row, 785 columns, and a matrix that's 785 rows and 10 columns. So if we do this kind of a matrix, vector matrix multiplication, we're gonna get a vector that's one row, 10 columns. Right. So the multiplication of these two is again one row, 10 columns, and the result are gonna be identical to the 10 logits that we obtained from the first approach. Right. So these two calculations are actually equivalent to each other. But the problem with this kind of calculation is that it's just for one training image. But in a mini batch, we have more than one training image, right? And in our code, the batch size for now is set to 100. So this x vector is really not a vector anymore, right? It's actually a matrix. It's a matrix with 100 rows and 784 columns, right? And every row represents one training image. And we have like 100 training images in one mini batch. So it's gonna have 100 rows and 784 columns. The weight matrix W, this weight matrix, it's not going to change with the batch size. So it is still going to be 784 times 10, right? 784 rows, 10 columns. So if we do this multiplication, x is 100 by 784. W is 784 times by 10. And then the result of this matrix multiplication is going to be a matrix with 100 rows and 10 columns. Right? It's going to be 100 rows and 10 columns. The bias vector B also is not going to change. It's still one row, 10 columns. Right? How this kind of summation is going to work out? How this component summation is going to work out? How can we actually do a component-wise summation between a matrix that's 100 rows and 10 columns and a vector that's one row, 10 columns? Right? And in fact, TensorFlow is actually intelligent enough to know about this problem. The team who designed the TensorFlow actually paid attention to this summation here, right? So if the calculation for one training example works out, it means what? It means that all we have to do is to just duplicate this bias term by 100 times along the row direction. We just duplicate this W, this B vector, this row vector, like 100 times along the row direction. We just have 100 rows of B, right? And then the component-wise summation is going to work out, and the result will be correct, right? But if you actually try to duplicate this vector, if the vector is quite long, it's not just the 10 categories, it's like a 100 category. If you duplicate like 100 times, that's a huge waste of memory, right? It's a waste of computational resources, right? So what TensorFlow is going to do is that it's going to handle this particular summation in a way as if the bias vector is duplicated 100 times without actually duplicating it, right? It's going to do a summation that's kind of sort of distributed along the rows, basically. It's basically just going to recognize the problem, and then when it actually do the summation, it's just going to sort of do something that's kind of similar to a loop. It's going to do a summation for every row of this matrix vector, the result of this matrix multiplication. So the result is going to have like 100 rows, then it's going to do this summation 100 times, basically, right? But without actually duplicating the bias vector B. Right? And if we actually use the second approach, as we did in solving the linear regression problem, we are doing that, right? We will not really have this kind of problem, right? If we have like 100 images, all we have to do is to sort of stack those images on top of each other. Then we have 100 row times 785 columns. And we don't even have to make any changes to the weight matrix at all. It's still 785 times 10, right? And this 100 times 785 matrix multiplied with this 785 times 10 matrix is going to give us 100 rows and 10 columns. That's exactly the logits for the 100 training examples in the mini batch, right? If we are using the second approach, we don't have to worry about how this summation is carried out, right? But the problem is that we have to waste a huge amount of memory for storing the first column, which is just a constant of 1. Right? There's no point in storing it. Right? That's sort of the trade-off. So when building our computational graph, so we will be adopting the first approach this time, right? With both the weight W and the bias vector B. And we will rely on TensorFlow to actually handle this plus correctly, this component-wise summation correctly. Right? We will not worry about that. Right? So now let's write the code to build the graph first. Right? So we're gonna first clear out all the nodes in the default graph. We just put the lines in the middle, and then we can sort of create 2 placeholders to store the input image data and the 1 hot encoded label data for each mini batch. So there are placeholders. Placeholder, it's going to be float. So we are not going to specify the row number. The row number is going to be any row number. In practice, it's going to be 100, right? Because our batch size is like 100. And then that's for x, and then y. Tf dot placeholder again. Float. Again, none. And then n class. This is for storing the one hot encoded label data for the training data set. Right? And this part of the code is actually identical to the linear regression problem that we have solved, and we can sort of compare it, right? So TF, so reset the graph and then the placeholders. But here it's like tf.float32. Here I'm just typing float to save some typing. And next we create 2 variables, one for the weight matrix, capital W, and then the other for the bias vector B. And we're going to initialize them to zeros. So I'm going to do a init equals to tf dot constant initializer value equals to 0.0. That's the initializer. And then I'm going to define W as tf dot get variable, and then give it a name capital W, and then the dimension n co and the n class. N co is going to be 784, right? N class is going to be 10. That's going to be the dimension. So 784 by 10, right? And then the initializer is going to equal to init. And then B equals to tf dot get variable. So B. And B is going to have a n class. It's going to be a vector, right? And then initializer is going to equal to init, right? So that's W and B. So in the linear regression problem, we only had 1 weight vector. That's defined here, right? That's a variable also, right? TensorFlow variable. Because the bias term was put on top of the weight matrix as in the second approach, right? Both approaches are equivalent. But here we're actually separating the weight into like a weight matrix and then a bias vector. And in the linear regression problem, we were initializing the weight matrix, the weight to random numbers, right? But here we're actually initializing everything into to 0. But this is not really a big difference. You can also initialize it to random numbers if you want to. But I'll just initialize it to 0 because it's something that I have tried before, so and it worked. So and then the next thing we have to do. So let's go back to the linear regression problem. After we have defined all the x, y, and the w, then we define the y predict. That's the model predicted y, right? That's the model predicted output, and we call it y underscore pred. right? For the linear regression problem, this y pred is just a matrix vector multiplication, just the x multiply the weight, the input data multiply the weight to a matrix multiplication, right? But here in this softmax problem, this logistic regression problem, we're gonna need more operations than just a simple matrix multiplication, right? We're still gonna require the matrix vector multiplication, matrix multiplication, but we also need to do a summation with the bias vector b, and then that's just gonna give us the logit, right? And then we need to feed the logit into a softmax function in order to actually get the y. So this time y pred is going to have a slightly more complicated expression. So here we're going to call the softmax function that's provided by TensorFlow. And then we're going to do the matrix multiplication, mat mal. And then x, that's the input data, with the weight, capital W here. And then we have to do the plus b, this summation, right? And we talked about this summation. This component-wise summation is not going to work out on math, on paper, but TensorFlow will actually handle this summation differently, as if this bias vector was duplicated many times to match the row number of this X matrix, basically. But it's not really gonna do it's not really gonna duplicate the data, but it's gonna have an effect that the result is going to be sort of identical to the situation where you actually have duplicated all the bias vectors like multiple times, many times. Okay. So, and the results of this very special summation, it's a very special summation here, and TensorFlow is going to handle that correctly, in the correct way, basically, right? The results of this particular summation are just going to be the logits, and to obtain the predicted output, we still need to feed the logit into the softmax function provided also by TensorFlow to actually get the y pred. Now with the predicted output, the y pred, we can now compute the cross entropy loss, right? If you don't remember what exactly is the cross entropy loss, back in video 8, we talked about this cross entropy loss. So this TJ, here TJ is the ground truth label converted into one hot encoding. That's TJ. And then we have to sort of do this kind of a component-wise multiplication with the log of the predicted y. Right, so how do we actually write that? So it's going to be, let's call it dot product. Dot product equals to, so in our case, the ground truth is actually inside of the tensor y here, right? Y multiply, this is the component-wise multiplication, tf.log, we're going to use the log function provided by TensorFlow, and then y pred. So here tj is the ground truth, and in our code it's y is our ground truth, and then y underscore pred is our model prediction, and here in the equation it's yj, that's the model prediction, right? So that's the dot product. That's a component-wise multiplication. Component-wise multiplication, it's not really doing a summation yet. So here there's a summation here, right? There's a summation over j. J goes from 0 to 9, right? And this summation is actually along the row. It's actually summing along the row. For every row we do a summation. And then every row is going to produce like one number, basically. And this particular summation can be done using a special TensorFlow function. And then the result, let's call it cross entropy, equals to minus tf dot reduce sum, minus tf dot reduce sum, and then dot product. This summation has to be row-wise, right? For every row we do a summation. So xs equals to 1. And we need to add the minus sign, right? We have a minus sign here. It's not just doing a summation. It's got a minus sign in front of it. That's the minus sign that we have to account for here. right? So that's accounting for the summation along the across the 9 columns for every row, right? And then we also need to get the average loss, cross entropy loss, over all training examples in the mini batch. So this averaging process is again a reduction, but it's a reduction along the column. So the average loss is going to equal to Tf dot reduce mean x entropy, right? So this loss tensor here actually corresponds to the MSE function, the MSE tensor that we sort of used. MSE was called the mean squared value, right? This was sort of the loss measure in our linear regression example, right? But here it's called a loss, but it's actually a cross entropy loss, right? And now we can, once we have the loss, we can define our optimizer and also the training operation. And this part is actually identical to the linear regression problem. So all we have to do is to just copy those codes over. Learning rate I have specified at the beginning of the script, so I don't have to sort of copy learning rate over. Right? And then optimizer just equals to tf.train. I'm using the gradient descent optimizer. And then learning rate equals to learning rate. Right? And then training up equals to optimizer minimize. It's not MSE anymore, right? It's called loss. The loss that we have just defined. And by now, all the nodes that's needed for training are actually defined. But this time in the linear regression problem, we didn't have a test dataset, right? But this time in this particular case, we have a test dataset, right? We also need some kind of node to compute the accuracy of our model or of our trained model on the test dataset, right? How are we going to do that? So it's actually easier than you think. Let's define a tensor correct prediction. It's called correct prediction. So this correct prediction is just going to be equal to tf.equal, and then tf.arg max and then tf.arg max y1, and then accuracy is going to equal to tf.reduce mean tf.cast. You have to cast it to tf float. No, not float. Right. So the correct prediction, this tensor that we define here, is what? It's just a straightforward comparison. So tf.equal is going to do a comparison. A comparison between what? This argmax is going to take out the index of this y-pred vector, which has the largest value. Remember that this is a one-hot encoded thing, right? So y-predict is going to be the probability. The value is going to correspond to the probabilities, right? So if the value is largest, which means that it's the most likely result, right? And the index, or the index corresponding to that largest value, is going to be the digit. Is going to be the our predicted digit of the handwritten sort of picture, right? So we're basically comparing the predicted digit with the actual ground truth digit. So if they are identical, then this equal is going to compare to true. If they are different, then this equal is going to compare to false. And then when we did this cast, it's going to convert those Boolean true or false values into ones and zeros. So true are going to be a 1, 0 is going to, false is going to be a 0, right? We did this cast into a float. And then this reduced mean is just going to do a summation and then do a average of all the 1s plus all the 0s together. And then that's going to be our accuracy. So if this accuracy is very close to 1, then it means that our training has been successful. And if the accuracy is very far away from unity, then our network is no good. And we'll write the codes for running the neural network, training and running the neural network, and testing also in the next video.